Hi, my name is Nathan Kutz. I'm a professor of applied mathematics at the University of Washington in Seattle. And I'm going to be talking today about the discovery of dynamics directly from data. So mostly what this talk is going to be about is how we can take modern machine learning algorithms and AI infrastructures and bring them into data collected from physical systems towards building models and thinking about how we can take that and really enrich what were our possibilities from the point of view of scientific discovery. All this work has been done in collaboration with Stephen Brunton, who's in mechanical engineering. He is my main collaborator here at the University of Washington, and I will feature much of the work of our fantastic group of students and postdocs who have been doing a lot of the groundwork on building out algorithms for physics and engineering machine learning. So most of this talk is going to focus around the idea of coordinates and dynamics. So whenever we start taking recordings from a system, what we would really like to do is find a representational frameworks or a coordinate system that is sort of in some sense ideal for representing some of the dynamics in the system. So I'm going to give a generic picture like this, which what you see here is I'm going to have input data, which is going to come, let's say, from sensors of the system, and I want to learn a coordinate mapping to a new variable, a latent space, in which I can represent that dynamics in some kind of efficient and potentially parsimonious way. So we're going to talk a lot about that process during the talk, but this is sort of this generic structure of getting into a coordinate system where I can represent the dynamics and then coming back out. And a lot of the talk is going to feature targeted use of neural nets towards doing a lot of work for us that is advantageous. So first of all, this idea of coordinates and dynamics certainly is not new, and it has a long history, and many of our coordinates that we have used in the past revolve around a lot of different kind of features that we know about the data. For instance, special functions have been widely used in mathematical physics for using it in the context of coordinate systems. Like for instance, if you're in a system with polar coordinates or spherical coordinates, there are representations and special functions that are actually quite ideal for representing solutions. For instance, many of the special functions out of mathematical physics, like Bessel, Hermite, Laguerre, are really sort of these ideal coordinate systems given a specific set of geometries. So you exploit that geometry in representing your solution. We also have a lot of expert knowledge. People who have deep expertise in many physical systems can leverage that expertise for understanding the physics in a nice way and having a good representation. More recently, there's been a lot of methods using SVD-based approaches. In other words, taking that data and finding a low-rank embedding in which to represent that data. So SVD-based methods are things like proper orthogonal decomposition. This also goes under the name of PCA, empirical orthogonal functions, Hotelling transform, lots of different names for the same thing, which is find a way to take your high-dimensional state space into some low-rank feature space and then build your model there. And more recently, now we have neural nets. Neural nets give us even more flexibility because they allow us nonlinear transformations into a coordinate system, whereas the SVD-based methods are all linear. So this is one way to think about coordinates. We've been doing it for a long time, finding good representations. And then once you're in this model space, once you're in now this new coordinate system, you want to represent the dynamics. And there's a lot of different ways to do that as well. I give you some here. There's, for instance, standard statistical methods for time series like ARIMA, autoregressive moving average models. There's more modern things like dynamic mode decomposition and Koopman theory, which tries to represent the dynamics in a linear fashion. One of the things we'll focus here too is on SINDY, which is the sparse identification of nonlinear dynamics, which means once I'm in this space, can I discover the governing equations that produce that data? And so there's these discovery methods that have emerged that we can now make use of. There's also things like trying to represent this in terms of normal forms in dynamical system setting. And also, when we think about taking time steppers, you could imagine once you're in this coordinate system and you have time series data, you can just use neural networks like LSTMs or current neural nets, GRUs, echo state networks, for actually doing forecasts of that in the time series domain. So lots of options for both building coordinates and also building dynamics. And so part of what we want to discuss is what are some ways to do this. And obviously, when I say good coordinates, this is a very subjective term. And so what I mean by good coordinates could be very different than what you mean by good coordinates. But I'm going to give you some examples in which I hope will really highlight what I intend when I say good coordinates. And we start here. So hopefully you can see this okay. This is the night sky. And what you're seeing here is snapshots taken over time. And what you're seeing here, this is the retrograde motion of Mars in the night sky. Okay? And then what you're seeing here, for instance, is the retrograde motion of Saturn in the night sky. So this is really remarkable. This is, in fact, the oldest of the physics problems, which is to try to understand the nature of the movement of the heavens, right? So celestial mechanics is sort of, in some sense, the canonical physics problem that was explored for centuries and generations, okay? In fact, millennia. And so what we want to do is try to understand, can we write down predictive models for the trajectories of the planets? And this was really sort of this big challenge problem that people had, but was of great interest to most of society. And so the earliest models of this actually go back all the way to Alexandria, Egypt, in the Claudius Ptolemy. This is the Ptolemaic dynasty, in which this was sort of the intellectual center of the ancient world, really before Rome sort of took over all of the Mediterranean region. Alexandria was sort of this intellectual capital, and out of this came the Ptolemaic version of a doctrine of the perfect circle. And the idea here was that you could actually think about the retrograde motion of the planets as circles on circles. So that was one way to represent the dynamics of those orbits and also do forecasts of where those orbits would be. This is kind of like the earliest theory of this, and in fact it was very successful. It lasted for 1,500 years until the time of Kepler and Galileo when it came down. And it also represents sort of, in some sense, a representational aspect, which is it's in some sense the earliest Fourier transform. So you can think of this data circles on circles. These are different frequencies, different orbits of these circles, which is very much like what you would do in a Fourier transform in terms of representing things in terms of different frequency content. So there's these amazing pictures from Renaissance times, and this is Renaissance Italy, showing sort of a map of the perfect circle theory in some sense. And so this is one of the longest lasting theories we've had. From the 2nd century AD all the way to right around the 1600s, this was the theory, and it's kind of like the Roman Empire of theories. It's one of the longest lasting. It's highly unlikely we'll have theories like this last that long in human history again. And what brought it down? It was still very accurate model, still is today, right? It's not like it's a terrible model. It does a pretty good job. The big change was to understand the coordinate system. And so here what I show you is that one way to understand the retrograde motion is if you change the coordinate system. In those times, the coordinate system was the Earth, everything was revolving around the Earth. And then there's Copernicus making the suggestion that in fact everything was going around the sun. And really this was backed scientifically by Galileo and Kepler and laying down the foundations for making the shift to the heliocentric coordinate system. Now the amazing thing is once you move this to this coordinate system, now you're set up for Newton to come along and derive and produce F equals ma. This beautiful theory about gravitation, but you had to be in the right coordinate system to push that theory forward. And of course, it's a great theory, and it lasted for many hundreds of years before we realized that there was the discrepancy between the data and those F equals ma models, which Einstein used to build out his theory of general relativity. And undoubtedly, as we get more and more accurate measurements, one can imagine that we're going to also go beyond general relativity. But of course, we would need the data to inform that physics-making process, just like Einstein's had the data to build that model. And what eventually happened is Galileo and Kepler also had the data finally to build this model and set it concretely in place for future generations. So this is what I mean by a good coordinate system. In a good coordinate system, the dynamics you come out are these nice parsimonious representation, F equals ma. And you don't find that until you get that good coordinate system to work with. There's also something to be highlighted here in the work of Kepler and Newton. Kepler essentially was using the data and doing a regression of elliptic orbits onto that data. He was fitting the data. He was fundamentally doing an interpolation task. Newton, on the other hand, with his F equals ma is inherently an extrapolatory tool. So for instance, Newton, once you have this, he could imagine things like, what if I launched someone from Earth to the moon and put them in orbit? This is something that F equals ma allows you to model. You've never observed it, but F equals ma allows you to understand the conditions under which that could happen, whereas Kepler was a regression onto the data itself. So this represents this kind of tension between the two, because in some sense Newton is the more famous of the scientists, partly because he built a model that allowed us to go places we've never seen with the data. And that's exactly kind of in some sense what I would like to do, and I think what a lot of physics and engineering practitioners wants to do is understand some principles and then figure out how to engineer new and innovative systems that I've never had collected data from before. By the way, these concepts of Kepler and Newton are alive today in some of our modern technologies. And I want to highlight here, these are our grand challenge problems that we see today. We have robots, self-driving cars, autonomy, right? Now notice what this robot is doing. This is a remarkable feat. This robot's doing a gymnastics routine. It's much more athletic than I am. It's actually just remarkable to watch some of these videos that come out of Boston Dynamics and what these robots are capable of doing. But it's also equally amazing to watch these self-driving cars that can navigate, through construction sites and through traffic and be on highways, be in cityscapes. And this is remarkable that these cars can actually navigate those very successfully. The interesting thing about these two autonomy paradigms is that in some sense they are very different from each other. They're both autonomy, but one is completely physics-based. So this robot technology is really imbued with F equals ma physics. It understands so much of its world through having physics models of the world. It understands momentum. It understands angular momentum. This is how it's able to walk and do its tricks. It has a physics engine inside of it, which is based upon all the physics we've built up to the modern time. So one way to think about it, it's imbued with Newton-type architecture. On the other hand, this car is not built this way. This car is built with a bank of sensors with massive amounts of training data, which is labeled to tell it what the environment is happening. And if you give it enough training data, it learns a representation of this world through deep neural networks. And so there's no physics per se, but it learns everything it needs to be able to successfully navigate the roads with given rules about how fast it should go, when should it brake, and so forth. And so in some sense, this is a regression to the data. I'm not going to make any comments about which method is better. Both these methods have experienced a tremendous amount of success in our current society. And it also reflects this tension that's always been there. And Bryman highlights this in the two cultures of statistics. One is to think about this as a statistical learning, which is trying to really get after the models of the primary idea. And this one here, more machine learning, which is building some representation that simply functions well and works well. Whether you have an interpretability or not is, in some sense, yeah, it would be nice, but that's sort of beside the point. You just want to make this thing work well. So these two are where we are right now, right? You can use different architectures. You can think about really imbuing with physics or just straight machine learning. And where I want to spend time in this talk is sort of at the in-between spot, which is you want to still use all the power of machine learning, but bring it over here to the physics world. How do you bring all this machine learning technology, but you still want to get interpretability and maybe have a shot at generalizability, getting some models that you can go to places and extrapolate. So here's the mathematical formulation that I want to give. I want to lay down fundamentally what we want to do mathematically. And this is it here. Here's the mathematical framework. I'm going to have some model, a dynamical system that produces the data I'm going to measure. F specifies the model. There's some parameters for it. It might have some stochastic effect. And X is the state space variable. What I actually have access to is a measurement. Y, T of K, these are discrete time measurements through a measurement model H. There's some noise on this data. Always there's noise. And so part of what the goal here is just simply, from the measurements, can I, in fact, tell you what the measurement model was, what the state space is, X, what the dynamics are, F, what the parameters are, theta. This is a terribly ill-posed problem. So normally you'd think we teach all of our undergrads and grads, avoid ill-posed problems. But as I'm starting to learn, what you really want to do is say, I'm going to have the really interesting problems that we're solving today are all ill-posed in many ways. And the whole idea here then is to say, if I want to solve these, what I really need to do is bring in appropriate regularizations and constraints to make it go from ill-posed to well-posed. And so I want to talk about the constraints I want to impose on this mathematical formulation, because that's really what it's about. I'm going to take this measurements and dynamics, it's ill-posed, and to make it well-posed, I'm going to really impose the idea that I want interpretable parsimonious representations of the dynamics. So in some sense, I would say the ultimate physics regularization is to figure out what the intrinsic dimension of the system you're measuring is, and the smallest number of terms, some kind of parsimonious or nominal representation of the dynamics. I mean, these ideas are old. They go back to William of Ockham, which he really was a proponent of nominal models. Include the things you need, but nothing more. And this has been said over and over again through history since that time, including by Pareto and Einstein himself. And so this is going to be our physics regularization. We're going to promote, in many of these architecture, sparsity towards giving us a nominal parsimonious representation of the dynamics, which oftentimes leads to interpretability and the ability to extrapolate. So that's where we're going with what we want to do. Find a coordinate system that this holds. Okay, so let's start off in a simple place. The simplest place maybe is I want to find coordinate transformations and a coordinate and dynamics transformations in which linear models are a good place to work with. So linear models are really nice because we typically can just write down the solutions to these linear models. We can say a lot of things about linear models, much more so than nonlinear models, obviously. And let me give you an idea of this. Isn't this going to go towards Koopman theory? And Koopman theory is all about thinking about a coordinate in which the dynamics becomes linear. We're not linearizing the dynamics. We're using a coordinate system to make the dynamics linear there. And here's an example of this. Here's a 2x2 nonlinear ODE. And so normally what you might say is like, well, OK, I can, I don't necessarily have, for generic 2x2 nonlinear ODEs, you can't write down closed form solutions, but you can look at fixed points, phase plane analysis. But here, notice that if I change variables to y1, y2, y3, which is given by here, which is x1, x2, x1 squared, then this model becomes perfectly linear. So all I did is made a coordinate transformation, and in this new coordinate, I have linear dynamics, and I can say everything that I want about the system. I can look at the eigenvalues, eigenvectors, write down the solution to this nonlinear differential equations problem by putting it in a different coordinate system. So that's the generic idea behind building these linear models. Figure out the coordinate system or an approximation to a coordinate system to make this work. So part of the way we do this is through, in this Koopman theory, is using a tool called dynamic mode decomposition to make an approximation to a linear embedding. So the idea is the following. I measure some complex system. So I have snapshots of that system. It could be high dimensional. And I'm taking measurements of it. And generically, it's some nonlinear evolution equation that gives that data. And what I do is I form some data matrices, x and x prime. So x are snapshots of that system over time. X prime are all those snapshots advanced delta t into the future. And so those are going to constitute my observables. I just take those measurements, and then what I do is I just say, build a linear model that takes me from x of n to x of n plus 1. So that snapshot x of n to x of n plus 1, and there should just be some linear matrix A that does that. But I have a lot of snapshots, so I want the best linear matrix that gets me through all of those snapshots from one to the next, delta t into the future. And so when you do this regression, it's just a least square fitting procedure. And in fact, there it is here. That matrix A of x tells me the best linear model through all the snapshots, which is just x prime times the pseudo-inverse of x itself. And that's what's called dynamic mode decomposition. It's a regression to the best fit linear model going through the data snapshots. What Koopman theory does, on the other hand, it says, why would I work directly with x? Maybe there's some observable, some change of variables, so I can go to g of x. So I don't work with x directly, but some observable of x. And I construct new matrices y and y prime, whose columns are the snapshots in this new observable g of x. Then I do DMD. So the hope here is if I can find the right coordinate transformation, then this linear model should work out pretty nicely. And this is exactly the example I showed you. If you make a change in your coordinate system, you can get a linear model. Okay? You're not guaranteed to get a linear model, by the way. There's more to be said there. But the idea here is we're going to approximate that with this algorithm, which is the dynamic mode decomposition. And here what we're going to do is we're going to figure out, well, how do I come to an observable set? We're going to use neural networks. So neural networks are going to try to learn a coordinate transformation to do this heavy lifting for us. Now I want to highlight here that neural networks, this is from the first sentence of a paper by Stefan Milat on understanding deep convolutional neural networks. Supervised learning is a high-dimensional interpolation problem. The key word here is interpolation. Neural nets live in the space in which you sample that data, right? Most of what we want to do in physics is extrapolate, I would say. So you're going to have some constraints here by using neural nets, which is within the data you've collected, you can build a model, but it tends to be over-parametrized and it tends to be very brittle and does not generalize well. This is well known, and people are working very hard at finding ways to loosen that up to make neural networks a little bit more interpretable, more generalizable. So here's where we're going to start. We're going to try to do this linear embedding by figuring out if the neural net can figure out the coordinate system for us. So you see what I'm doing here. I'm pairing a coordinate system with dynamics. The coordinate system is some transformation. The dynamics, I'm going to force it to be linear. So we're going to learn how a neural network, an encoder, take us from our original variable to new variable y, and then back. And what do I want to have happen in this new variable? When I go from snapshot y of k to y of k plus 1, I want there to be a linear map that does this. So I want to learn some linear operator in conjunction with the coordinate transformation so it's true. If I take 2 steps in the future, it's k squared in this new variable. All this work was done with Bethany Lush. So Bethany Lush really pushed this forward. And so she started engineering these architectures to do exactly this structure here. And so we started this, and we started thinking, well, let's try to embed the nonlinear pendulum in some linear coordinate system. And we failed. And it's actually, in retrospect, quite obvious why you would fail, because, in fact, the pendulum, the oscillations of the nonlinear pendulum, the frequency changes over as the oscillations get bigger. In fact, if you want to see this, here it is here. This is, as you take larger and larger amplitudes of the oscillations, here is the shift in frequency, and it does one other thing. It generates harmonics. And this is well known from asymptotics from the 60s. So you can take the Duffing equation and you perturb it. You find as the perturbation gets bigger, what you find is the frequency shifts. You generate third harmonics, and there's fifth harmonics, and it's a little bit easier to see the fifth harmonics here, and then there's a seventh harmonic. And this is all due to the nonlinearity producing these extra frequencies. And then the shift in the frequency is also due to the nonlinearity as well. So this is interesting, and it highlights something very important. We were trying to embed the pendulum in a 2-dimensional space because we know the pendulum doesn't change dimension. It's still 2-dimensional. But look how many frequencies you need to represent it. Because of the continuous nature of the spectrum, You can't represent, a 2x2 system can only have a complex conjugate pair, so a single frequency, and this requires many frequencies to represent it. So instead, we modified this neural network architecture. So if you want to keep a linear model that's at the intrinsic rank of the dynamics, then we learned a second network that parametrizes that linear operator as a function of the frequency. So once you do this, build this linear model with parametric dependency, everything works just fine. And so, in fact, you can start looking at embedding the nonlinear pendulum, which you can see here some of the dynamics with very large amplitude oscillations. The dynamics is not sinusoidal. It starts to really become more exotic looking than sinusoidal. And you can basically take your dynamics, which is embedded in nonlinear space, to embed it in a completely linear space. So that's really nice, right? So you're saying I can actually take very large amplitude oscillations, embed this, and still make it linear if I just warp the coordinate systems, and these are sort of your eigenfunctions, as it were, to make this transformation happen for you. So we were very happy with this. We can go to harder models, something like flow around the cylinder. This is when you have von Karman vortex shedding on the back end of that cylinder. And the same thing. You find that if you look at the dynamics back there, there's some low-rank structure. You can take that time series, which is generically some nonlinear dynamical system, and we can embed that in a linear dynamic model. And here is the linearized dynamics. Here's essentially your eigenfunctions for this transformation. So what we've done here then is be able to take this flow around the cylinder in this von Karman vortex shedding regime, find a coordinate transformation to make this linear. So that's the idea, in some sense, behind Koopman theory. We took this even further, and this is work with Craig Jin. Craig did this. I'm still surprised by this, but this is kind of amazing. So we started looking at more complex PDEs, and I didn't think this could be done, but the code's here. The code's on GitHub. You can run it yourself. But we basically take something like the Kerr-Moda-Shivasinsky model, which produces spatial temporal chaos, very complex dynamics. And by learning this neural network transformation, and it's a little bit more complicated than the original neural networks we did, this thing we can learn in embedding to take this PDE and make it linear in this new variable. So this is quite remarkable. This is like the inverse scattering transform, which linearizes the KdV or NLS equations. Here, we can just do it with, as far as we know, generic PDEs. If you can do it with Kerr-Moda-Shivasinsky, it gives you a lot of options, because that's a very difficult equation. And here's some of the results of that. You can run the full PDE and look at our linear embedding and back out into the original variables. And it works marvelously well. So you can find that up on the archive, actually. So that's kind of the idea behind linearization. And of course, we don't have to make linear models. In fact, sometimes linear models are a little restrictive. So maybe what we should do is start thinking about, like, how do we make more general models? And so we want to allow maybe to go to just discover governing equations that can be nonlinear. And so how are we going to do this? So we're going to relax this assumption about linearity. Because nonlinearity is a fantastic way to parameterize dynamics. And so what we're going to do here is use this method called the sparse identification of nonlinear dynamics, or what we call SINDY. The idea here is this is just going to be an AX equal to B problem. That's the math. An overdetermined AX equal to B, where we're going to promote sparsity. Here's how it works. If I give you data, in this case XYZ, time series of XYZ, you know that dynamics was generated by some x dot equals f of x. Well, if I give you XYZ, you could compute the x dot. That's B in the AX equal to B. The matrix A is a set of candidate right-hand side functions. So it's x dot equals f of x. F could be lots of different things. You can pick up all your physics books out of the library and look at what kind of models have people built over time in history. Well, there's lots of different models. And for all the different terms in those models, you can put them in as candidate functions in this right-hand side. So you say, here's a library of potential right-hand sides. And I'm going to regress on this equal to x dot, which you computed. Now, if you do a standard regression like least square fitting, it will take all those library elements and it will weight them, all of them, a little bit to try to fit the data. However, if you use sparse regression, what it will do, it will say, OK, I'm going to find the smallest number of library terms possible to fit the data. In other words, the derivatives, the x dots. And so what it does, by promoting sparsity, and we do this by sequential least square thresholding, we don't use things like lasso because they tend to be pretty unstable algorithmically. If you do this, you find here are the non-zero terms that show up. And those non-zero terms are, in fact, the Lorentz equation. So essentially, if I sample that data, I can tell you what the dynamical system was that produced it. So we built on this architecture to go to things like spatial temporal systems, like PDEs. And here, this is work with Sam Rudy. And Sam wrote this paper where he basically did a bunch of different canonical PDEs out of mathematical physics. And here they are, KdV, all the way down to Navier-Stokes. And here's the question. I just give you spatial temporal data, so snapshots in space-time of these systems. Can you tell me the PDE that produced them? And Sam's method is just basically using that SINDY architecture on spatial temporal data. So now you've got to compute spatial derivatives. And in fact, you can discover all of these. And different of these systems can tolerate some amount of noise more than others. And so that's also a study that Sam was able to do to see how robust this is for being able to discover partial differential equations. So this is a nice discovery tool, right? So if I take measurements of a system, you can tell me what the governing equations were. So this is a really nice framework to come to new systems to try to understand dynamics and build models from them. Where I think this is actually even more applicable, however, though, is in what's called discrepancy modeling. So the idea is that there's very few problems that we come to anymore where we know nothing, right? Where we just have no principles, we don't understand anything about the physics. In most systems, we have some partial knowledge about the physics. Maybe we don't know everything. Maybe our model is, here's some things that are true, but we're missing a bunch of physics. But generally, we do know some things. So discrepancy modeling is a framework in which you can say, I want to come to the table with an imperfect model. So here it is. I know some physics. It just turns out that that's not good enough to represent the dynamics of my system. What I really need is some kind of correction to the physics. Well, the SINDY architecture I just showed you, it's trivial to handle this. Because if you know some physics f of x, you can just move it over here to the left. So you get x dot minus f of x. That is now my new vector, b. When I do that ax equal to b regression, the b just takes in the f of x. You still regress to a library of terms to try to model what's missing. It's as simple as that. This architecture of SINDY is very flexible. And you can even put constraints on it very nicely with the ax equal to b. You can enforce things like conservation of mass or momentum. It's a very flexible framework, and it's just ax equal to b. Okay, so it's a nice architecture. Now, where does this play a role? Well, let me give you the example here. These are pendulums that are on a cart, double pendulum on a cart. And if you just give it the Platonic knowledge of physics, what I mean by that is perfect mass measurements, no friction, no air resistance, then it's very difficult for this thing to actually stabilize the pendulum. But if it can learn the mismatch between its model and the actual data, you can improve that model by building in the discrepancy to stabilize that pendulum. And this is especially important for things like the digital twin. So I'm showing you here a digital twin, which is this is an emulation, this CAD emulation, of an actual robot. Now, they look pretty close, but when you do precision manufacturing, you are not afforded the luxury of being close. You have to develop a model here that really matches very closely that model there. There are frictional forces and sticking of the joints. If you allow this thing to learn that discrepancy model, for every single robot, each one will develop its own discrepancy and get you a better match between the emulated model and the actual digital, which is the digital twin, and the actual experiment, right, or the physical manifestation in the world. So this architecture allows you to say, I know most of the physics for this. I just need to correct for it to match that specific robot there. And so this SINDY architecture is a flexible framework for doing such a thing. I mean, you can also use Gaussian process regression models and so forth, but those are just statistical estimates, whereas this is actually trying to build a model for what's actually creating the discrepancy. Okay, so in a lot of what I've talked about here so far, I've assumed that I actually took measurements of the system and I knew what the state space was. What happens if I have, though, a model where I'm taking measurements, I don't really know what the state space variable is? So here I want to discover jointly the coordinates and dynamics. And those, I even have to discover the state space. And this is what we talked about at the initial part. And so this is work with Kathleen Champion. And Kathleen really kind of solved this problem in framing it in the following way. What she said is, look, if I have measurements of a system, I want to learn a coordinate transformation. And what I want to have happen in that coordinate is I want there to be a parsimonious representation of the dynamics. So we're going to put a SINDY model in the inside of that autoencoder structure and then be able to come back. And here's sort of what the loss function might look like. And then you can train this thing. Now this kind of architecture is exactly what I talked about at the beginning with the celestial mechanics. If you observe the night sky, the first thing you have to be able to do is recognize what the appropriate coordinate system is, which is the heliocentric world, and then discover f equals ma here. So this is what this part of the neural network does. It discovers there's a heliocentric world. Here, f equals ma. And they come in a pair. Another good example of this is if I give you a video of a pendulum. So like I film a pendulum. What I give you for data is pixel space. There's no way for that pixel space to know that there is this coordinate theta and theta dot that represents the dynamics of the pendulum. So what this would do is take pixel space, learn that in fact this thing should go to a coordinate system that's embodied by theta, theta dot, and then within that coordinate system, theta double dot is sine theta. So that's the idea behind this kind of architecture. It's really powerful, and it's exactly what we tend to do when we do physics, which is, can I find that coordinate system and then I get a good representation of the dynamics? This is doing both. You're learning them simultaneously. And so here's some different examples of this. I just want to highlight the bottom one, which is the nonlinear pendulum. If I just give it videos of the dynamics, it discovers theta, theta dot, and it discovers that theta double dot is sine theta. That's kind of remarkable. So it gives us a way forward when we think about all the kind of instruments that we're using nowadays to measure physics, right? Which is a lot of imaging techniques. And so we need, the image itself doesn't necessarily give you the right coordinate, but this gives you an architecture in which you can get to the right coordinate and build the model that you need from there. The other thing that's interesting about this, that inner layer has the potential for generalizability, whereas the coordinate system, you know, like if I double the length of the pendulum in the video, that coordinate no longer works. But what I learned, the theta double dot sine theta, still holds. So maybe I can pin this generalizable physics and then just learn a new coordinate system if I change the length of the pendulum. So these are very nice things to think about in terms of what's generalizable in a model, what's not generalizable in a model. We can build on these ideas and just think about what else can we use targeted neural nets for. And I want to talk here about a couple other themes that we've built on, and one of them is just time coordinates. So what if we just say, well, if I'm in this time coordinate, I could build a dynamical model, a linear model, or this nonlinear model, or maybe I could just regress directly, because really what I want to do is forecast some data. And so this is work with Henning-Lange. And what we started building is thinking about Fourier and Koopman forecasting. And the way this works is, if I want to go into the future with some process and look, say, make a prediction long time into the future, we have very few functions that long time in the future don't blow up or go to zero. And sines and cosines are perfect because they persist to infinity. And so I want to do is take data, time series data, and you could say, well, a simple thing to do is fit it to Fourier modes. And what you want to do here, of course, unconstrain it so it doesn't satisfy a periodic bound condition, but fit it to Fourier modes. We take one extra step, which is we also say, what if we were to take whatever data we have, make a transformation, do a coordinate transformation in time to make these time series data look more sinusoidal, then fit it to Fourier. And that's exactly what Henning did, is this Koopman forecasting is to learn a coordinate transformation in which sinusoidal functions are really ideal. So this paper is appearing in the Journal of Machine Learning Research, And you can take these more exotic looking functions, and we do an amazing job of forecasting, for instance, for a long time, systems that have sort of periodic, quasi-periodic behavior that are kind of exotic long time into the future. And in fact, if you compare it against other standard techniques, and the standard techniques I would say come from two sides. One, from things like ARIMA, so time series analysis out of the statistics literature, or neural networks out of the computer science side of things. And if you just compare this kind of forecasting, Koopman forecasting trick against them, it beats all of them for long-term forecasting. For a very short time, delta t into the future, many of these do quite well. But for a long time, this is almost unbeatable. It allows you to do a lot of things with model building, including things like this, building low-rank models without even simulating a system anymore. So here's the ground truth of some PDE. I can reduce this down into some low-rank subspace with an SVD, look at the time series of that, and just fit it to Fourier modes and almost do a perfect reconstruction of this, and also then provide a prediction to the future state. And I'm not even simulating a PDE anymore, right? I'm just simply doing a projection, doing a long-term forecast, rebuilding the system, which is much more efficient than almost any reduced order modeling architecture, because you're actually not solving or projecting the dynamics onto some sequential stepper in time. You're just, once you got the model, forecast as far out as you want, rebuild. And this is exactly what this does. You can also think about how you want to handle multiscale physics. There's a lot of flexibility in handling multiscale physics, including architectures such as this, where Yu-Ying Liu is a grad student, where he started to exploit transfer learning and multi-grid architecture for computation, in which he uses a convolutional neural net to look at the coarse-grained features of the data and refine and learn new features only in the regions where it's necessary. So you have this progressive refinement in the architecture in which you refine only where necessary. So you start with a coarse-grained representation and you go to a finer representation, but not everywhere in your domain, just where you need to. And this gives you this ability to learn very rapidly because you transfer the learning from one level to the next to be able to refine the models as you go to a multi-scale spatial architecture such as this. So neural nets have amazing flexibility when you put them in sort of these innovative architectures. They can do a lot of flexible things. You can also solve boundary value problems. So we've been talking mostly about time, but you could take all of this technology and frame it back into thinking about boundary value problems. So this same architecture I exhibited above, or in most of the talk, where you have an encoder to a latent space, then you do dynamics. Now, instead, we have this encoder, and we do something with boundary value problems. And a lot of this was done by Dan Shea, where not only has he taken data from an unknown boundary value problem, transformed it, and found parsimony representations for that boundary value problem. In other words, discovered the boundary value problem. He's also found representations of the Green's function. How do I learn a coordinate transformation to linearize this process so that what I get in here is a linear boundary value problem, and I can construct the Green's function and then come back out. So this is, all these architectures solve a lot of our classic problems that we have. In fact, all of the methodology you learned in classes that are sort of classic techniques, many of them can just be brought right over into sort of these modern architectures, and with suitable adjustments and modifications of the neural networks, made to work in a very nice way by using targeted neural network structures. So I'm going to end here, and basically my conclusion here is that this parsimony idea, this nominal representation of the physics, is, I think, the ultimate in physics regularization. And I think it gives you the best shot at interpretability. It gives you the best shot at extrapolation and generalization, partly because you have a very, what you end up with is a model with a small number of parameters that parameterize it. So the idea is to discover models from data, and this is the generic architecture, which is, it's all about coordinates paired with dynamics. So I'm going to leave you there, and I hope you have found something interesting in this talk. And I would, again, encourage you, I don't think can be much controversy around the idea that if you have a good coordinate system, that's probably going to be a really great way to represent your dynamics. And so all I've talked about is using some of these machine learning methods to try to help aid in that discovery process, which hopefully would help you do a better job in understanding many of your engineering and physics problems that you're looking at.